Hello students, I am Professor Priya Kulkarni and I am here with the last unit, that is finite element method. Okay, finite element method is a numerical method which gives approximate solution for all the complexities of problems like varying shape and boundary conditions. Varying shape means we have seen the numericals or we have seen the problems in our structural analysis part 1 and 2, the having a definite shape, that is a beam or any frame or any truss, that it means it is having a definite length and definite shape. It means vertical, horizontal, or in incline or x direction or y and z direction. So we have not seen any complex structure. For example, I will give you a cooling tower. Okay, you have seen the cooling tower. So it is not having a definite shape, or it is not exactly vertical. It is having curves and it is having various amount of uh, 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 dimension or diameter changes. Bottom diameter is different, top diameter is different, and it is having a curvature. So in short, for the problems or for the structures which are having a complex shape or complex dimensions and uh, complex boundary conditions also. Okay, we have seen definite boundary conditions, that both end fixed, one end fixed, another hinge, like that, roller, cantilever, like that. We know all these 4 to 5 type of boundary conditions, but apart from this there are certain boundary conditions which we have not studied here. Okay, so finite element method comes to rescue us. So here we are going to study and actually it is a numerical method and it is very easy method for the analysis or for the problem solving for varying shape, boundary conditions and loads. The basic philosophy of this method is to replace the structure or continuum having unlimited or a finite number of unknowns at a certain chosen discrete point. So what we are doing, we are going to distribute or we are going to divide the structure into certain discrete points, and accordingly we are going to analyze the structure. What do you mean by analyze? Same thing we are going to do here. We are going to draw or we are going to find the shear forces, bending moments, stresses, strains at that particular structure. If it is a cooling tower, then we can calculate thermal stresses also. If it is aircraft, okay, aircraft is also having a variant uh, uh, indefinite shape. Okay, so for and so and one more thing, this finite element method is also for the mechanical branch students. Okay, so we are going to use the software like ANSYS, STAD Pro, okay, for the civil students. So STAD Pro and ANSYS, they have their basic idea or they are programmed according to finite element method. Okay, so if you see the STAD Pro or ANSYS software, the first step or first page is it is divided into grids. Okay, the first window or what we call say the first screen that comes, it is divided into screens. So this type of screen will get if we open such a software, for example STAD Pro. Okay, so these on these grids we are supposed to locate our nodes. Nodes means it is a point of particular dimension or particular direction. Okay, so we are going to distribute our structure into particular nodes. So this the idea behind STAD-Pro and ANSYS is finite element method. Okay, then okay, so first thing is it is used for varying shape and boundary condition. The next important point is the fast improvements in computer hardware technology and splashing of the cost of computer have boosted this method. The fast improvements in computer hardware and technology and slashing of cost of computers have boosted this method. Since the computer is a basic need for the application of this method, a number of popular brands of finite element analysis packages are now available commercially. Okay, so we have STADPRO, Nastrian, NISA, and ANSYS. Using these packages, one can analyze several complex structures. Okay, then finite element analysis is originated as a method of stress analysis. Okay, so we are going to analyze the stresses basically. In the design of aircraft, it is started as an extension of matrix method of structural analysis. Since we have used flexibility matrix and stiffness matrix method, we know how to form the matrix and what are the contents of that particular matrix and idea behind the stiffness and flexibility matrix. We know this much part, so we can or one can easily form a finite element matrix. Okay, so today this method is used not only for solid mechanics but even for the analysis of fluid flow, heat transfer, electric and magnetic fields, and many other civil engineers use this method extensively for the analysis of beams, frames, plates, shells, folded plates, foundations, rock mechanic problems, and seepage analysis of fluid through porous media. Okay, so there are numerous applications of finite element method. Both static and dynamic problems both static and dynamic problems can be handled by finite element analysis. So this method is extensively used for the analysis and design of ships, aircrafts, spacecraft, electric motors, and heat engine. Okay, so there is a wide range of applications of the finite element method. Now, what is the main idea or main principle behind this method? It is, we know that force, or it is the relationship between the force, displacement, okay, and stiffness. So we know P is equals to K into delta, or we know stiffness is equals to, it is the force required to produce unit displacement. Okay, so we know this relation, P is equals to K delta. Okay, so here we are going to use the same concept, that P, that force F is equals to K into D. Now this E, what suffix we have used here is the at that particular point or at that particular node. Okay, so this is the main idea behind, this is the main idea behind the stiffness, or finite element analysis, that stiffness into displacement is equals to force. Then now since this last topic contains much theory part, so I have just gathered all the important theory over here. Okay, and since our exams are going or will be conducted like multiple choice objective questions, that's why I have gathered lot of theory over this PPTs. Okay, and I have written notes also. I will upload it in Google Classroom and I'll share in a WhatsApp. So just use or refer these notes. This is much theory part, and we can score good marks in this unit. Okay, what is the difference between the finite element method and classical method? So classical method, exact equations are formed. Okay, exact equations are formed and exact solutions are obtained, whereas in finite element analysis, exact equations are formed but approximate solutions are obtained. Since the structures are not in a regular or in appropriate shape and boundary conditions are also different, that's why we get the approximate solution. Okay. Solutions have been obtained for few standard cases by classical methods. Okay, this is one more uh, plus point that we have, that in classical methods we get the solution of some standard cases only. We cannot solve other cases. So, but in finite element method, we can analyze all type of problems. Whenever following complexities are faced, classical method takes a drastic assumptions that shape, boundary condition, loading. So we have assumed in the starting that it is for definite shape like that. Okay, So the assumptions are not here in the finite element analysis, since it is free for all the shapes and for all the boundary condition and all the complexity. Okay. To get the solution above cases, rectangular shapes, some same boundary condition along a side and rectangular equivalent loads are to be assumed. So in finite element method, no such assumptions were made and the problem is treated as it is. Okay. When the material properties is not isotropic. So if you remember, the first assumption in every structural analysis theory or any principle, the first assumption is this material is isotropic, homogeneous, linear, non-elastic. Okay, we have assumed this part and we have sorted the structure. But here in finite element analysis, even if the structure is not isotropic, solutions for the problems become very difficult in classical method. But few simple cases has been tried successfully by researcher, and finite element method can analyze all with isotropic and anisotropic properties without any difficulty. Okay, so this is very much advantage in finite element method. So what do you mean by isotropic? Isotropic means it has the same properties in all the three directions. Okay, that is isotropic. And if the structure consists more than one material, it is difficult to use classical method. Okay, but in finite element we can use one more than one material complex problems without any difficulty. And problems with a material and geometric non-linearity can be handled by classical method, but there is no difficulty in finite element method. Okay, so whatever assumptions that I have used in the classical method, that are uh, solved by the finite element method. Okay, so this is the basic difference between the classical method and finite element method, proving that finite element method can solve all the complexities. So this is the same continuation of the previous slide. So it has shown in this diagram for irregular shapes, irregular boundary conditions. Now see here for change in boundary condition in the certain length. Okay, so in our classical method we have not solved any such a problem with this type of boundary conditions. Okay, and irregular loading. Okay, we have standard loading cases and accordingly we have formed deflection and rotation equations. Okay, but in finite element method no such a limitations are there. Okay, now the main important part and the actual unit starts with a discretization of the structure. The first and important step in finite element analysis is to generate the mathematical model. By using finite number of discrete elements, it should be as near as possible equivalent to actual continuum. So, these elements are connected to adjacent element only at the limited number of points are called nodes. So thus the idealization of continuum or discretization of continuum, we have to decide number of shapes, size, configuration, elements in such a way that the original body is represented by weight as close as possible. Hence, the general objective of such idealization is to discretize the body into finite number of elements sufficiently small so that simple displacement model can adequately approximate the true solution. So what does the discretization means? It actually means that we are going to divide our structure into finite, okay, finite number of nodes. Okay, and we are going to solve the no, the particular structure or particular numerical problem, and we are going to find out all the unknowns over there. So what this I have first diagram says, this is a bar, okay, first bar, and we have divided this bar into number of nodes, okay. So these are the nodes mean points where we are going to find out the particular displacement by load, deflection, forces, stresses, like that, okay. Then what is the discontinuity of load? Again, this is for this discretization is for irregular shapes also, and for this irregularity of loads or discontinuity of loads also, okay. So elements are attached to adjacent elements only at the nodal points and have constant material properties, okay. So anything, any structure, any bar, any truss, any portal frame, any dam, any retaining wall, any water tank, any cooling tower is divided into a number of finite nodes so that to form a mesh, and we are going to analyze our problem by using finite element method. So there are various uh, steps for analyzing the numerical. So this is so see this example of dam. This is dam we have shown here, and it is divided into finite number of nodes. So this numbering what you are seeing here is the nodes, node number. And see this is shown here is a material discontinuity, okay. So first is material 1, second is material 2, and it is again divided into number of particular finite nodes. And here discontinuity of boundary condition, here also we have divided. So this is, now we know the shape of the structure, it is rectangular, so we have divided into 4 nodes, okay, like that. Now one more important term while we are going to discretize our structure is the element aspect ratio. So what does it means? Now here see this first diagram, it is a rectangular structure, and we have divided this structure into 12 nodes, okay. So it is actually, okay, so element aspect ratio is lengthwise nodes divided by widthwise nodes, in means nodes, okay. So lengthwise we have here divided into 12 units or 12 nodes or 12 parts. It is having a certain unit like meter, foot, like that, so we are considering here units. And in widthwise it is divided into 1 unit, okay. So what does the aspect ratio here? Here actually the aspect ratio, so next point is element shapes. So based on shapes of element can be classified as one dimensional element, two dimensional elements, axisymmetric elements, and three dimensional elements. So these are the element shapes, okay. So we'll see one by one. So and these elements are suitable for the analysis of one dimensional problem may be called as line elements. So one dimensional elements are line elements, they are having only one dimension. So as you can see here, okay, so all the elements are having x direction. So these are the one dimensional elements, okay. So these elements are suitable for the analysis of one dimensional problems, and these elements are basically called as line elements also, okay. Next is two dimensional elements. So here we need two dimensional elements, okay. to solve the two-dimensional problems, obviously. So common two-dimensional problems in a stress analysis are plane stress, plane strain, plane problems, okay, plate problems. And two-dimensional elements are often used as three-noded triangular element shown in the figure, and it has a distinction of being the uh, first and most used element. Okay, so these elements are known as constant strain triangle, CST, or linear displacement triangle, LST. Okay, so constant strain triangle and linear displacement triangles are mostly used two-dimensional elements. Okay, so this is in X, this is Y, and it is a constant strain triangle. It is having three nodes. Then linear strain triangle, it is a 6-noded 10-noded triangular element. Okay, now see here the same triangle is divided. Now first in constant strain triangle, that triangle is divided into 3 nodes, and in linear strain triangle it is divided into 6 nodes. Okay, it is divided into 6 nodes. And one more strain triangle is quadratic strain triangle. So it is having a 10 number of nodes. Okay, so 6-noded triangular element is known as linear strain triangle, and 10 noded triangular element is known as quadratic displacement triangle. And as you can see here, this node is called as interior node or internal node, and all the boundary nodes are known as external nodes. Okay, these are external nodes and this is internal node. Okay, so these are very much used, and these are mostly asked questions in the exam. So there are higher order triangular elements also having a maximum number of nodes as 15, 21, like that. So they are known as quadratic strain triangles. Okay, so they are known as quadratic strain triangles. Now this is one more part is there, the element shapes. Okay, so you can see here, so this is divided into 15 nodes, maximum 15 nodes, and it is divided into 21 nodes maximum. Okay, so they are known as cubic strain triangle and quadratic strain triangle. Now here the some we have seen this about the triangles. So there are rectangles also in element shapes in two-dimensional. Okay, so these are the some basic rectangles with 4 nodes, 6 nodes, 9 nodes, 21 nodes, likewise. So there are also some, see, as you can see here, these are known as quadrilateral elements. Okay, so even higher order triangular elements may be used to generate the quadrilateral. So this quadrilateral is divided into triangles for the convenience, or for to solve the easily or simplicity. Now there are not only triangles, rectangulars for definite shape. We have curved two-dimensional elements also. So we can analyze the curves also. So this is cooling tower shape. Okay, so this is curve. Okay, parabolic curve. So we are going to analyze this type of curves also by dividing the curve into particular nodes, finite nodes. Okay, then we have seen one dimensional, two dimensional, then there is a axisymmetric elements also. So what does the axisymmetric elements? So these elements can be constructed from one dimensional or two dimensional elements, and the structures formed by revolution of surface or revolution of curve are called as axisymmetric structures. So it may be either solid or shells or maybe of axisymmetric. So it name itself is meaningful that axisymmetric. So axis symmetric, okay, it is symmetric about the particular axis. It may be in x direction or y direction, so one dimensional or two dimensional, like that, okay. So for example, a thick cylinder, circular footing on soil mass, pile foundation, cooling towers, water tanks, circular shafts, chimneys are the example of axisymmetric elements. So these are the element shapes. These are a three-dimensional. Okay. So these are the three-dimensional shapes. So whatever dot dot part you are seeing, it is in the x direction, in the third direction. Okay. So hexahedron, rectangular prism are the examples of these three-dimensional elements. Okay. So this again this helps in the finding the uh, stresses for curved dams, stress distribution in soil, curved beams, thick press vessels where problems are not idealized. Okay, so we can use three-dimensional elements also here. So as we have seen, nodes are primarily or secondarily. So just uh, for the sake, so see this first diagram, 1 and 2 are primary nodes and 3 and 4 are internal nodes. Okay, similarly 1 2 1 2 and 3 are known as primarily nodes. The 4 5 6 7 8 and 9 are known as secondary nodes, and 10 is known as internal node likewise. Okay, so nodes are primary, secondary and internal nodes. Okay, so we'll see next is our superparametric, isoparametric and subparametric elements. So we'll see in the next lecture. And we have plane stress and plane strain problem, one short uh, uh, solution of the plane stress and plane strain problem. Then there are shape functions. So shape function is important part of this finite element method, and then we'll cover our whole syllabus, and we'll go for the some revision, or if you have any doubts you can ask me, and then I'll be having one MCQ exam of 50 marks. Okay, and then we have our final exam. Okay, so best of luck and start studying all the units that we have covered from first to this last unit. Okay, so all the best and be prepared, and don't forget to mark your attendance in the comment box. Thank you.